Alright, this video series we're going to take a more in-depth look at the actual shape of molecules and how different molecules have different shapes, and this is a first step into looking at this concept of polarity in molecules. So we won't quite go there with this video, but the learning goal for this video is to understand this thing called hybridization of orbitals. And how to draw simple Lewis structures and to determine the shape of some simple molecules. In order to fully understand what we're going to discuss in this video, it's important that you've gone through the series on electron configuration and energy level diagrams, and have a good understanding, of course, of Bohr molecules. Make sure you also follow along with the handout that you can get off the website titled Hybridization and Lewis Structures. So what we're going to do is we're going to take a look at the chemistry of carbon. Carbon, of course, has an atomic number of 6, which means it has 6 electrons surrounding the nucleus. And I've drawn sort of the simple Bohr diagram here. Of course, there would be 6 protons and 6 neutrons in the nucleus as well. These red dots, of course, represent the electrons. And the 2 electrons here that we see here, of course, are in the 1s energy level. And it's a full energy level. We've got our top one, our bottom one, and just drawing on the energy diagram. And I could also show them here on this orbital diagram. So I could throw one right there and one right here. And this is this right here is the 1s orbital. Now, these inner electrons, of course, do not factor into any reactions that a carbon atom would have. So they're there, we've known them, but we're going to move on. What we are interested in is the 4 electrons in the second energy level. And of course, Bohr's model is very simple. With Bohr's model, we know that there are 4 electrons in the energy in that second energy level, and we show them as you can see here in Lewis dot diagrams. However, we know, based on our lessons, that the electrons wouldn't exist in these flat spaces rotating around, because the law of electric charges states that like charges repel. So the electrons will try and get as far away from each other as they can. So we know we can stick 2 electrons in the 2s energy level, and that's this one right here, which means we have 2 more electrons to account for. And so, based on our understanding right now of our theory, we could say that, okay, we'll put 1 electron here, and maybe we'll put another electron here. And so we have 2 electrons in the p orbitals, the 2 p orbitals. If I were to show the electron configuration for carbon, it's simply 1s2, 2s2, 2p2. Now, we've gone through this, it makes sense. We understand that p orbitals are designed in these funky dumbbell shapes because electrons want to maximize their distance away from each other, which minimizes the repulsion that they feel for each other. And every time an electron feels the presence of another one, we could say its anxiety goes up. I mean, it feels some pressure, and that pressure translates to energy. And these electrons want to get to the lowest energy states possible, so they'll arrange themselves in this way. However, the problem with this model is that, number one, it doesn't fit what actually happens in terms of reactions. If we look at this model here, just looking at the energy diagrams, it would appear that carbon could only make 2 bonds. Because these would be the only 2 bonding electrons, because these guys right here would not want to bond. They're paired up. Why would they want to bond? So carbon would only be able to make a bond right here and a bond right there. But we've taught you since grade 9 that carbon makes 4 bonds, and we know where it is on the periodic table. It's 4 steps away from a noble gas, which means it would either share 4 electrons, or it could take 4 or lose 4. Of course, it's in the middle, so it would share. But if we look at this model right here, it doesn't make any sense. Plus, we have this open orbital right here that's completely empty. So now we have to retrain our thinking. So one of the things we have to think about is symmetry of charges. And this is going to play in later when we start looking at the shapes of molecules and whether they're polar or not, whether there's regions of negative charges and regions of positive charges, and that's for another video. But we can see that this molecule, the way we've drawn it right here, is not very symmetrical. It is with the two s orbitals, but my p orbital, I've got 1 electron here, 1 here, and none there. Doesn't make for a really symmetrical atom. So let's flip over to the next page and actually take a look at how carbon does bond and what type of molecules it makes. Now let's take something as simple as methane, CH4. We know that 4 hydrogens attach themselves to a carbon. So these black orbs right here would be a hydrogen atom, and the blue orb right here would represent carbon. And we know that we get 4 hydrogens attached. And this model right here actually shows the way that they are attached. Now we would typically show methane drawn out like this. You may have seen it drawn like this, say on in a textbook or something like that. And when we look at it this way, it looks like we've got bond angles of 90 degrees. And it looks flat. But in real life, it turns out that it's not. It's 3-dimensional. So we have a 3D model right here. Now we're not going to get into these angles per se, but they're bigger than 90. They're just over 100 degrees, in fact. And if we were to draw this out on pen and paper, it would really look something more like what we see here. This is a much better model. Where we've got these 2 sticks. These guys represent bonds between hydrogen and carbon. And this dotted line is telling us that this hydrogen is sort of going into the page, whereas this hydrogen is coming out of the page. And the angle between these 2 hydrogens and these 2 hydrogens and these 2 hydrogens and these 2 hydrogens and these 2 and these 2 and this one and that one and so on, all the angles are identical. They're not 90, they're over 100. But how do we explain this? How do we explain that carbon makes 4 when, if we flip back, based on the orbital model, the way that things are structured in the periodic table, carbon should only make 2 bonds? Well, it turns out, to quote the great Cosmo Kramer, a great thinker of the 20th century, Mother Nature is a mad scientist. And what Mother Nature does is has found a way. This is typically what we would perceive the electron configuration would be for carbon. However, in order for carbon to make the bonds that it wants to, and to get its electrons to the lowest energy state that they can be, what happens is this process called hybridization. And what hybridization means is that we take a s orbital and the 3 p's, and we steal a little bit of energy from the from the p's to bump up the s, and we drop down the p's just a little bit. So you can see that we've got a drop down and a bump up, and what we end up getting is what we call the sp3 orbitals. And in sp3 orbitals, there are 4 of them. And that allows 4 electrons to hop into these orbitals. And this means that because we have 4 electrons, we can have 4 bonds. Which allows carbon to minimize the energy of the 4 valence electrons and to maximize the distance that they're away from each other. And it turns out is the reason why biological systems are as complex as they are. Carbon has almost an infinite possibility of combinations between itself and other elements, and it is carbon which is the backbone of all biological compounds. And it's all because of this hybridization allowing for 4 electrons to be at a pretty low energy state, but all 4 of them to bond. And this sp3 orbital looks like this. It's a funky little dumbbell that's fat on one side and short on the other. And what happens is we get 4 of them. So this is what we would call an sp3 orbital, and we would have 4 of them. So we'd have one like that, we'd have another one that would look like that, another one that would look like that, and another one that would look like that. And we would say that, say this one is going into the page, this one right here is coming out of the page towards us, and these 2 are kind of flat. It turns out that the bond angles between these guys are all 109.5 degrees. And this is one of the things that you'll have to memorize, is that when we have sp3 hybridization, we get these bond angles at 109.5. And the shape that this takes on is called a tetrahedral. Tetrahedral shape or configuration of these orbitals. And so if I have an electron here, and an electron there, and an electron there, and an electron there, I've now maximized the space that these electrons have moved away from each other. And one really big thing, it's completely symmetrical. And that's big, because if you're asymmetrical, that means you have regions where you have more electron density than others. And so those regions, the electrons would be at a higher energy state. We know electrons don't want to be there. So we can take this model and apply it to these 2 representations of the molecule of methane, and we can see that we've got the bond angle, 109.5 degrees. And we can see that here as well. And all 4 hydrogens are at that same angle. And so this is our starting point for understanding shapes of molecules. And so we can start to predict what the shapes of the molecules are going to be, what their bond angles are going to be. And this comes into play with a lot of biochemistry later on, especially in university. So now we're going to look at a new model for Lewis diagrams. So we can see what our hybridization model looks like. We've got 109.5 degrees. The Lewis diagram for carbon would look like this when we write it on paper, but in reality we've got this tetrahedral shape, if you can imagine this to be like a pyramid. So we've got our triangle, we've got our triangle, we've got our triangle on the back side and on the bottom side. And so we've got these this pyramidal shape here. And so the new model for methane would look like this if we use just sticks here. So each angle 109.5. These red dots, of course, are representing hydrogen, and what we would have between them is is the shared electron. So hydrogen would share one electron with the carbon. Now hydrogen's electron, of course, would still be in the s orbital. So I'll just quickly draw that in so you can see what that's going to look like. So hydrogen's electron still is in the s orbital, but it can still make that bond here, which is what we're seeing here. I'll just highlight the bond. The bond between hydrogen's electron and one of carbon's electron. Here's the nucleus of carbon right there. I'll just pop that in black here, just so that you understand there's carbon's nucleus right there. And so this electron here would still spend some time, even out here, but most of the time it's bonded or paired up with this electron. In some molecules we have pairs of electrons. In other molecules we have lone pairs where we might have two electrons kind of hanging out by themselves together as if they've been paired to another atom. But this is our new model for methane. This is exactly what methane would look like if we were to use a ball and stick diagram. So what we're going to do now, that you have an understanding of this weird thing called hybridization, we're going to apply it now to, we're going to first take a look at how we can draw Lewis diagrams, so understanding how we can draw molecules, and then learning how to predict what shapes, because when we draw them, we're going to draw them as flat things on paper. We typically don't draw them like this because this is a little messy and difficult to draw and that. So we draw flat structures, but we still need to understand what the angles are. So now we're going to take a look at how we go about drawing Lewis structures. So what we're going to do is we're going to go back to methane. And what you need to do is make sure you follow 4 steps when you go to draw a Lewis structure. So we're going to look at how we actually come to something like methane, and then we'll apply it to a couple other diagrams. So the first step we do is whenever you go to draw a Lewis structure, you determine how many electrons you're going to need to arrange within the molecule. And so we'll show that right here. So we know that carbon has 4 electrons in its valence shell. Hydrogen only has 1. Now we've got 1 carbon, as we can see here, but we've got 4 hydrogen, so it'd be 4 electrons times 1 to give you carbon's share, and 1 electron times 4 to give you hydrogen's share, what they're both bringing to the pot. So 4 electrons total from carbon, 4 from hydrogen, gives you a total of 8 electrons. So now once we have that done, we want to pick the element or the atom that's going to be the central atom, and we're going to fill its octet first. So what we do here is we pick carbon to be the central one because there's only 1 carbon, and we know it can make 4 bonds, and we put the electrons around carbon. So we go 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 electrons around carbon. That fills its octet. Now, there are some elements that don't quite follow this rule. Beryllium can be a central atom and only have 2 electrons around, or 4 electrons around it. Boron is happy with 6. So there are some exceptions, but we're going to stick to the basics right now. We'll work on the exceptions later. So we've got our 8 electrons around carbon. Your next step would be, if you have any remaining electrons, to put them around the other atoms. In this case we don't, so this one's a little bit simple. Now, every time you have a pairing of electrons between 2 atoms, that represents a bond. So the last stage is to, wherever we have these pairs, put a line or a stick between the atoms to represent that there's a bond. Sometimes we can have 2 sticks together, which would be a double bond. Sometimes we could have 3. So in this case here, we've got 4 different bonds, and there we go. We'll take a look at another example here, and this one is silicon dioxide. And what we'll do is we'll look at each stage quickly here. So our first stage, of course, is to determine the number of electrons that each element is giving up. So we have silicon, it's got 4 electrons in its outer valence, and only 1 atom of that, so a total of 4. Oxygen has 6 electrons in its outer valence. We have 2 of them, so it's going to donate 12 electrons. So now we've got 16 electrons to deal with. So we pick our central atom, which of course is going to be silicon because there's 1 of them, and we put the 8 electrons around silicon so that it's got its full octet. Our next stage is to put the remaining electrons around oxygen. Now, we put 8 electrons around silicon. There's only 16 there, so we can see. So we only have 8 more to play with. What you need to think about is sometimes you need to keep things symmetrical or balanced on each side. So we put 2, 4, 6, 8 electrons around the oxygens. Obviously, these oxygens are not happy because they do not have a full octet. They only have 2, 4, 6 electrons. They need 2 more to satisfy their octet. So, you're probably thinking that maybe these guys right here might come into play. And sure enough, that's the case. These lone pairs up here don't stay as lone pairs. They end up coming over and adding to the bonds. And so what you end up getting is double bonds. So this lone pair would come here and create 2 bonds. There's one right there, and there's the other one. And this lone pair would come here and make 1, 2 bonds right here. And so this is what silicon dioxide looks like. We've got double bonds between the silicon and the oxygen. Now what we're going to do is go up here, and what I would like you to do first is maybe pause the video right now and see if you could figure out the number of electrons in play for water and sulfur trioxide. See if you guys can take a second here, pause it, and see if you can figure this chart out. Okay, so you've paused it. Let's take a look and see how you did here. So hydrogen in water, there's 1 electron, but we've got 2 hydrogen atoms, gives up 2 electrons. Oxygen's got 6 electrons, only 1 of them, so a total of 6, which gives us a total of 8. If we look at sulfur trioxide, we have 6 electrons from the sulfur. We have 6 electrons from each oxygen. There's 3 of them, so that's a total of 18. Now we have 24. So let's follow stage by stage each step, to determine what these molecules will look like. So in the case of water, we need to pick a central atom. Now we know we never pick hydrogen as a central atom because hydrogen can only make 1 bond. So it's obviously got to be oxygen. And we'll put the 8 electrons that we know oxygen is going to want around the atom. And then we'll pop the 2 hydrogens in there, and it turns out that we only have 8 electrons to play with. So step 3, again, we don't really have to worry about it. So step 4, we will put the sticks in. And there you go. That's what water looks like. We'll talk later about what these lone pairs do to the shape, but because hydrogen only needs 2 electrons to satisfy it, like helium, we only need 1 pair. You wouldn't see a double bond if you had hydrogen. Now let's go back up to sulfur trioxide. This one's going to be a little bit more interesting. There's 3 oxygens, 1 sulfur, so we'll pick sulfur to be the central atom. We'll put the 8 electrons that we know it needs around it. We'll pop our oxygens on here, We'll just put them like this. And we'll now start adding more oxygen. So we added 8. There's 24. So we've got 16 more oxygens. So 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've got 24 electrons here, but this oxygen does not have enough. So what I'm going to do is just copy this and paste it right there. And we'll try and determine what's going to happen next. So we know we've got this lone pair right here. And what that lone pair can do is it can come down and make another bond, just like we had seen with the silicon dioxide. So what we get is 2 electrons still around that oxygen, but we've got a double bond there. And the other oxygens retain their 6 electrons as lone pairs. Now, the thing about this is that this lone pair can jump from here to here to here, and there's technically 3 different shapes, or 3 different ways we could draw this. Now, chemists are lazy. We don't like to do more work than we need to, especially writing things out, putting dots and letters and things like that. So what we'll do is we'll put a bracket around this, and what this tells us is that this is what's called a resonance structure. And a resonance structure means that this double bond can jump between these 3. We've just drawn one form of it, but it will actually rotate from one to the other, and that's one of the the weird things about nature is that this double bond does not actually stay there. It rotates through, and sometimes you'll see resonance structures that look like this. So sometimes you'll see in textbooks where they use dotted lines to represent a resonance structure, and they won't bother putting the extra lone pairs around the oxygens, just to show you that this double bond is really in flux. It's jumping around. But for our purposes, just drawing this would be fine. Gray 11, that's good enough for us. So we can see that in some cases we have single bonds. Other cases we have double bonds, and it's even possible to have triple bonds between atoms. Now what we're going to do now is learn how to predict the different shapes of molecules, so that if I give you any type of molecule, you'll be able to determine the shape of it. I'm just going to move this guy over here, and we'll go on to the next page. Now again, make sure that you're following along and writing these notes out as we go, and with the handout. So what we're going to do is this chart is going to be something that you need to try and put to memory as best that you can. Really, really important chart. This is as far as we go with grade 11 in my class. Now in grade 12 we go further. There's a lot more shapes out there, but these are the 5 basic shapes that we're going to go through in grade 11. Now what I want you to think about is whenever you approach looking at a molecule, after you've drawn out the Lewis structure and you need to determine the shape of it, you need to ask yourself how many charge centers are there around the atom. Now a charge center is either a bond or a lone pair. That's a charge. Both of them are charge centers. Now it turns out that they both kind of do the same. And when we get down to 4 charge centers, it's going to force the shape of the molecule to go into a 3-dimensional shape, which takes us all the way back to this idea about this weird shape that carbon can take with hydrogen, this tetrahedral. Configuration. All right. So we'll definitely come back to that because we can see here we've got 4 charge centers. In this case, there are 4 bonds. So let's go back to here and let's look at some of the easier ones. Now, say you only have 2 charge centers around your central atom. So what does that look like? Well, in one case, it could be something like beryllium chloride, where you've got a molecule that looks like this. Again, beryllium's a exception. Beryllium can be happy with just 4 electrons around it. It doesn't need to have 8, so it doesn't follow the octet rule. So when we look at beryllium chloride, this is what this would look like. And we can see that there's only 2 charge centers. One bond is one, the other bond is another, and so it creates a linear shape. We could see something like this with CO2. Carbon dioxide, if you were to draw out its Lewis shape, you would notice that there are 2 charge centers. Now you don't say, oh wait, there's 2 bonds there. You count the double bond as 1 charge center, and this double bond as another. Okay, if it was a triple bond, it would still only be 1 charge center. Alright, so don't worry, the number of bonds doesn't matter. If they're together, you count that as 1 charge center. Now we've got 2 charge centers. It flattens the molecule out, and so we again have this flat line that we see here. And so both compounds are linear in shape. The bond angles are around 180 degrees. Alright? And we could just, for our purposes, say they're 180. It all depends. If I had oxygen here and sulfur here, it would change up the bond angle slightly, but that's something for university, not for us to worry about. Okay, so again, a charge center is either a bond, could be a single bond, could be a double bond, could be a triple bond, but a bond is 1 charge center, or a lone pair. Now another example that we can have is if we have 3 charge centers. So if we look at boron trichloride. So again, boron's another atom that doesn't quite follow the octet rule. It's happy with 6 electrons around it. And we can see here that we've got the 3 charge centers. And another one that we just looked at was sulfur trioxide with the resonance structure. Now what these guys will do is, because we've only got 3 charge centers, it flattens out the compound, the molecule, and their angles are approximately 120 degrees. Again, depending on the symmetry. You know, if one of these was fluorine or iodine, it would tweak the angles a little bit. But we've got flat molecules here, and the angles are, we'll say, 120 degrees. And we call this trigonal planar. Alright? So that's this shape. So these are pretty straightforward. Linear, straight line, trigonal planar, or planar triangular, sometimes it's called. We know that it's in one plane, it's flat like a pancake, and we've got these little triangles here. Alright? So three atoms, outside atoms in a triangle. Now where things get interesting is when we have 4 charge centers, because we have different possibilities, different permutations or combinations with charge centers. This comes back to this concept that lone pairs are also charge centers. And what that means is that a lone pair can act like a bond in terms of pushing bonds away. Whenever we have 4 charge centers, I'm just going to flip back to the old model, that means we have taken a tetrahedral configuration with our electrons. We've hybridized the electrons so that they are approximately or close to 109.5 degrees. Now this angle may get lower depending on if we have, say, a lone pair here or 2 lone pairs, But what you need to get stuck in your head is that if you have 4 charge centers, you're going to have hybridization taking place. Alright? So we'll take a look at a simple one that we've seen already. Alright, and this is methane. We have 4 charge centers. All 4 charge centers are bonds. We have no lone pairs here. The bond angles are 109.5 degrees. The shape is tetrahedral. That is the shape of this molecule. Now, what if one of those charge centers was a lone pair, like in the case of ammonia? Ammonia has, when you draw out the Lewis structure, we have a lone pair that's left over. Nitrogen has 5 electrons. Hydrogens each have 1. So there's 8 electrons in play, and we've got these 2 guys that are left over. This lone pair is still going to force these bonds to be pushed in a 3-dimensional space. We think of it as pushing them down. So even though we only have 3 bonds, we have a lone pair. So the molecule is not flat because here we only have 3 charge centers. Here we have 4. You have 4 charge centers. The orbitals are hybridized. Because this is a lone pair, it's not quite 109.5, it's 107, but all you really need to know is that it's above 100 degrees. Alright, it's 100 degrees or above. And what this means is that we've got a pyramidal shape because we've only got 3 bonds for the charge centers and 1 lone pair. It's a trigonal pyramidal shape, meaning we've got like triangles. Alright, 1, 2, 3. And these 3 make a pyramid. The lone pair doesn't show up. We can't see it. It's still forcing the bonds down. But it makes the molecule, the nitrogen, hydrogen atoms, take a pyramidal shape that's got 3 points. We call it trigonal pyramidal. So if you have 3 charge centers that are bonds and 1 charge center that's a lone pair, your shape is trigonal pyramidal. Boom, done. There's one other situation, and that is if we have something like with water. If you draw water out, again, there's 6 electrons coming from oxygen and 2 from the hydrogen. That gives us a total of 8 electrons, and we just did this one on the sheet before. But we've got 2 lone pairs and 2 bonds. So again, we have 4 charge centers total. 2 charge centers are bonds. 2 are lone pairs. So these lone pairs are still going to force everything to go into 3-dimensional space. So we're still looking at hybridized orbitals. The shape is bent. In the case of water, the bond angles are 104.5 degrees. So we're getting closer to 100. The lone pairs kind of squish them in a little bit more. But some of them are 103.5, some are 103. But anytime you have a bent molecule, it's because you have 2 charge centers that are bonds, 2 that are lone pairs. Alright? So again, these lone pairs, they still act as a charge center. And if you have 4 charge centers, everything's in 3D shape. So it's either you've got tetrahedral you're working with, trigonal pyramidal, or bent shape. Okay? So these are the 5 for our grade 11 class. These are the 5 main shapes that we worry about. Of course, in grade 12 we go a little bit further and we look at, there's more shapes out there, but for grade 11 this is as far as we go for our class. So the next video we start to take a look at how things like lone pairs and how things like electronegativity, which we've talked about in previous class, can create molecules that are highly polar, like water and ammonia, where we've got negative regions and positive regions. Or we have molecules like methane, or like carbon dioxide, which are completely nonpolar. We don't have a positive or negative side. So that will be our next set of video lessons.